Thank you for the lovely introduction. So today I have the honor to present to you our tool that we've been developing for almost a year now. And it's called, as you can see now, yes, Library of Brain Glycans. It's a resource for researchers in the field of neuroglycobiology. It's still under the review in Frontiers in Molecular Biology, Molecular Neuroscience, and we hope that we will have it published soon. So what are we going to talk about today? So today I want to present to you the background and motivation of why we built this tool, what is the current state of the field, and why we thought that it was needed. Then I will take you through the database features and the design of the database. So how it was developed, why certain things are made a certain way, and how it all fits together. Then we will, of course, cover the limitations, because no tool is perfect and neither is our tool, and we are aware of some limitations. And of course we will touch also on the future directions, on how we plan to address these limitations and to keep them at a minimum. So let's start with the first part of our lecture, and its background and motivation. So first, the background, of course. Thomas already gave a nice lecture on phosphorylation and its importance in brain glycans. And yes, I would like to start by prefacing that organs have a unique glycosylation pattern, which is tuned to their specific physiological functions, and most organs in the body exhibit their own characteristic glycosylation pattern. And the brain is exactly like that. So as we can see in this image here, conserved core network consists of, makes up 75% of the total brain and glycome, and the region-specific or species-specific glycans make up 25%, or 1/4 of the total brain and glycome. This is also further expressed because the brains and glycome is highly distinctive, because it has certain, as you can see, certain structural features that are unique to the brain, like A motives, Lewis X motives. We also talked about phosphorylation, which is much more common in brain glycome, and you can see other specific structures that are brain related. But that leads us to the question, how truly unique is the brains and glycome? And to answer that question, and to try and answer that question, we looked towards the data published by Helm and colleagues a year ago in Nature Communication, where they did comparative and glycomics of 20 mouse tissues. Which exact mouse tissues they analyzed, you can see here in this list. I'm not going to go through the entirety of the list, but I would like to highlight 4 most common ones. So kidney, brain, colon, and seminal vesicles had the most organ-specific glycans. And so what is very interesting for the brain, whether we're looking at organ-specific, so in both replicates, or possibly organ-specific or nominally organ-specific and glycans, brain took the 3rd position. So we can say with positive security that brains and glycome is very organ-specific and very different from the rest of the organs. So knowing that, what is the current state of the art in neuroglycobiology? So as we've already stated, brain glycans are highly diverse. They're often very specific, and I will also now add an information that they are also absent from general databases, and they require a bit more specialized tools simply because of those different features that they exhibit. And the existing tools often do not include common glycans, and this is something we've encountered when we tried and connect our database with Glycan database, Glycan repository. It was lacking, and we had to enter a lot of the brain glycans manually in order to be able to connect them. And even if they are showing, for example, brain glycans, or if they are labeling glycans that they were found specifically in the brain, they still lack some analytical information or chemical information or literal information. So there are multiple layers of information that are useful and necessary for you to create the entire picture. And to combat that and to help solve this issue, we've developed our library of brain glycans. You can find it on this website, and you can also use our QR code to take you directly to the website. So our goal was to systematically catalog all the glycans found in the central nervous systems. They include chemical, biological, and bibliographic metadata, and I will touch this multiple times over this lecture, so you can remember it for later. Its core idea is to function as an atlas for brain glycans, and it's an initiative of Human Glycome project. And as you can see, you can find it on the Human Glycome project website. So we can continue. So once we've covered the whys, now we can go into the hows. And now I will tell you about database design and the features. So first thing I want to cover is the criteria we use for selecting the glycans to go into the database. So I would like to separate these criteria into two main parts. So the first part would be the biological criteria, and the second part would be analytical criteria. So the biological criteria focuses more on the location of the glycans, so they have to be CNS glycans, of course, but they can be both from in vivo and in vitro origin. And the glycans that are planned to be included are the glycoprotein glycans, glycolipid glycans, and glycoRNA glycans, but currently the database is limited only to N glycans released from glycoproteins. When it comes to analytical criteria, also we need some kind of standardization, because if we start combining different methods, different labels, different strategies, it's going to become a mess and it's not going to be comparable, and in the end it won't be that useful. So in order to combat that and to help our database be more useful and more in line with this idea, we limited it to procaineaminide labeled glycans with assigned normal phase glucose units, or GU values, determined by helic UPLC analysis. Also, our database supports silation-specific derivatization. And here in our database, we currently have two examples. So ethyl esterified and methyl amidated linkages for NEU5AC. And that leads us directly into the design of the database. So it's a curated database, so it means that somebody had to manually go through all the data that once went into the database. It's structured, it's made to be expandable, so once we have new knowledge, once we have new glycans, or for example, if you want to add additional layers of information into the database, we can do so. It's built on a relational database model. It's probably the most common way of designing your database. It has, as I said before, 3 layers of information. So the first is the glycan chemistry, which is the mass, composition, GU values. Next is the biological context. So it's the species, information on the tissue, developmental stage. And finally, we have literature data. It's where the glycans were published. So the study name, DOI, and the authors. So it can be all linked. So, and one last thing that is very important to mention is that it was developed with FAIR data principles in mind. So the FAIR data principles tell us on how the data should be described in a database. So it should be easily findable and accessible. It should be interoperable, so any other database that could potentially use that data can access it in a fair way, and it should be reusable, which we try to achieve with our database. Moving on, so this is the diagram of the database. So in the middle, you have the chemistry. So this is all the basic information we have on the glycans. On the right side, we have the literature information, and at the top, we have currently implemented biological information. Of course, at the bottom, we have two more next future prospects that we want to implement into our database. Mainly the diagnostic fragments, for which the infrastructure already exists on the database, and pathology, whose infrastructure currently doesn't exist on the database but will be implemented in the future. But at the moment, if you try to search the database, you won't find any information on these two items. So it's plans for the future. So what do you do when you come to our database? So the first thing you will see is our search bar. So you will see a welcome screen that lets you enter, and then you will get this nice smart search bar. It lets you search multiple query types. So for example, if you want to search by our LGB ID, you can do so. You can do it by glycan ID, by composition, by species, by organ, structure, or study. So there are a lot of different things you can try and filter your desired information on. It also supports fuzzy searches. Fuzzy searches are searches when you don't type completely correctly a word, but the search will allow for some mistakes. For example, if you write humna instead of human, you will still get results for human because it's close enough for it to be searched. Also, one important thing that people usually look over is the wildcard search. So it's if you press a star or if you send an empty request, you will get the entire database listed for you. When it comes to the results, they are organized inside this nice table. The good thing about the table is that it's customizable, so you can tailor the data that is being shown to you based on your specific need, and you're not forced to see information that you don't really need. Next, besides the search options, you also have filtering options. There are different filtering options. You can see them listed all here. So it's species, organ or region, so brain, cortex, or maybe if it's organoid, for example, it will be listed here once we have them in the database. Next is the stage of life, brain specificity, so if there are brain-specific glycans, you can choose so. At the moment, we have 17 of them. Then study, mass range, geo range, so these are ranges. And once you type your desired range, you will press OK, and the database will filter out glycans only in your desired range. And next in line is the detailed view. In the detailed view, we prepared our detailed description of the glycan, and the description is divided in the same sections that I told you about. So GU units, composition, mass, then biological information is in the expression profile, which has species, taxonomic ID, which connects it to a PubMed database of species, then studied group page, because Glycome can change based on age of the studied model species. Then we have tissue of origin, brain region, and Uberon code for the region of organ. We also have included some standards from GlycoStore, which are used as internal standards for the database. And yeah, I forgot to say, finally, at the very bottom, you will find the study of origin, or literally metadata, where you will have the study title, journal, year of the published study. You will have the DOI and the name of the last author of the study. And next, the final thing that we need to talk about when talking about the design of the database is the curation, versioning, and API. First thing is the curation. So as I said, at the moment the database is manually curated. This ensures accuracy and consistency of the data. Also, we would like to preface that community contributions are welcomed and you can access them via Contact Us in the footer. We also started versioning our database. So once, for example, once you do a study or take some information from the database, you can always go back to the version from which the data originated, and we will keep all the major versions in our database. And last but not least is the API. API allows you to connect to our database with your software or your code and to directly mine the data from the database without needing to deal with the GUI. So what are the limitations? I already mentioned some, or at least hinted some. So the first one I would like to mention is the methodological constraint. So focusing only on glycans derivatized with ProA and assigned HeliQ PLC GU values limits these options. But as we said, this limitation is at the moment necessary to ensure the quality of the data that is inside the database. And the next one is data coverage. This limitation should be updated in due time with all glycans, glycolipids, and glycoRNAs planned in the future versions to be included. At the moment, it reduces the complete data set available in the database, but again, it ensures that the data that we currently have is higher quality and thus more useful to the end users. And for the future perspectives, again, we touched on some. The first thing we touched already on is the expanding scope, so I will not talk about that again. The next thing we have to mention is continuous updates. Like any software, this database is going to be a living resource, which means it will evolve, develop over time, not just in its contents, but also in its technical expansions. So we already have some UI UX improvements in the works, and we also have some structural upgrades in the works that I already showed you. Community contribution is going to be very important. So one team cannot fill the entire database. We need contributions from the community, from researchers all around the world to send their data, and so we can include them in the database so we can make the tool most useful to everyone. And the final thing that I also hinted on but didn't really talk about is the curation evolution. So currently the curation relies on manual work, but if the amount of information coming our way becomes exhausting and significant, we will implement semi-automated pipelines that will scale the curation process. And to finish, I would like to acknowledge all the members of my team that helped us develop this tool. I would also like to thank Jaspero for helping us with the UI UX, and I would also like to thank the organizations providing funds to our project. Thank you, and if you want to, you can find our resource here. Any questions?